The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right, so yesterday in the recitation we sort of talked a little bit about how to debug programs on Cell. Today I'm going to talk a little bit more about sort of debugging parallel programs in general and give you some common tips that might be helpful in sort of helping you track down problems that you run into. And as you might have sort of gotten a feel for yesterday, debugging parallel programs is harder than sort of normal sequential programs. So in normal sequential programs, you have your traditional set of bugs, which parallel programs inherit. So that doesn't get much harder, but then you add on new things that can go wrong because of parallelization. So things like synchronization, things like deadlocks, things like data races. So you have to get those right. And now you have to debug your program and figure out how to do that. And one of the things you'll see here is a lot of tools might not be as good as you'd like them to in terms of providing you the functionality for debugging. And add to that bugs in parallel programs often just go away if you change one instruction in your, or one statement in your code, you reorder things and all of a sudden the bug is gone. It's kind of like those pointer problems in C where you might add a word, add a new variable somewhere and the problem's gone, or you add a printf and the problem is gone. So here it gets harder because those things can sort of get rid of deadlocks, so it makes it really hard to repeat, have an experiment that you can repeat and come down to where the problem is. So what might you want in a debugger? So this is a list that I've come up with. And maybe if you have some ideas, you'll want to throw them out. But I'm thinking in terms of debugging a parallel program, what I want is a visual debugging system that really lets me see all the processors that I have in my network, in my multiprocessor system. And that includes the actual computing and the actual network that's there interconnecting all the processors that are going to be communicating with each other. So I'd like to be able to see what code is running on each processor. I'd like to see which edges are being used to sort of send messages around. Might want to know which processors are blocked. That might help me identify deadlock problems. And for these kinds of scenarios, it might be tricky to sort of define a step because there's no global clock. You can't sort of force everybody to proceed through one step. What's one step on one processor might be different on another, especially if they're not all running the same code. So how do you actually do that without a lack of, without a global clock? So that can get a little bit tricky. And it likely won't help with data races because I'm sort of looking at global communication problems. I'm looking at trying to identify what's deadlocked and what's not. So if there are data races, this kind of tool may or may not help with that. But in general, this is sort of the tool that I would build for debugging. And I looked around on the web to see what's out there for debugging parallel programs, and I found this called TotalView. This is actually something you have to buy. It's not free. I don't know if they have evaluation licenses or licenses for academic purposes. It kind of gets close to some of the things I was talking about. You have processors. It shows you communication between those processors, how much data is being sent through. This particular version uses MPI, which we talked about in previous lectures. So it's sort of helpful in being able to see the computation, looking at the communication, and tracking down bugs. But it doesn't get much better from there. How many people have used printfs for debugging? It's probably it's the most popular way of debugging, and even I still use it for debugging some of the Cell programs we've been writing. I know the TAs actually use this as well. And yesterday you got first a hands-on experience with GDB. And GDB is a nice debugger, but it lacks a lot of things that you might want, especially for debugging parallel programs. You saw, for example, that you have multiple threads. You need to be able to switch between the threads. Getting the context right, being able to name the variables is tricky. So there's a lot of things that could be sort of improved. And there are some research debuggers, like something we've built as part of the Streamit project, Streamit Debugger. I'll show you some screenshots of those just so you can see what we can do. So in the Streamit Debugger, remember we have, so this is actually built in Eclipse, and you can download this off the web as well. And you can look at your stream graph Unfortunately, I couldn't get a split join in there, much to Bill's dismay. So you can't see, for example, the split join and all the communication, but each one of these is a filter, and if you recall, the filter is a computational element in your stream graph, and they're interconnected by channels. So channels communicate data. And so what you see here, you might not be able to quite see it, you actually see the data that's being passed through from one filter to the other. And you can actually go in there and change the value if you wanted to, or highlight a particular value and see how it flows down through the graph. If you had a split join, then you might be able to, in fact, you can't do this. You can look at each path of the split join independently, and you can look at it in sequence. And because the split join has nice semantics, it's actually, you can replicate the behavior because of all the static nature, so everything is deterministic. So this is very helpful. We did a user study 2 years ago almost with some like 30 MIT students who used this debugger and gave us feedback on it. And one of the things, so we gave them like 10 problems, 10 code snippets. Each of them had a bug in it. We asked them to find it. And so a lot of them found the debugger to be helpful in being able to track the flow of data and being able to see what goes wrong. So if you had, for example, a division that resulted in NaN and not a number, floating point division, you can immediately see it on the screen, so you know exactly where to go look for it. Doing that with printfs might not be as easy. So sometimes visual debugging can be very nice. Unfortunately, visual debugging for the cell isn't that great. So this is the cell plugin in Eclipse. I've mentioned this to some of you. If you want to run it, you can run it from PlayStation 3, but if if more than one of you is running it, then it becomes unusable because of memory issues. You can install this on other Linux machines and have remotely debug on the PlayStation 3 hardware. So they can, the two remote machines can talk through GDB ports. I can talk to you about how to set that up if you want to. But it doesn't really add anything over Emacs, for example. It just might look fancier than an Emacs window or a GDB on the command line prompt. So this is the code from yesterday. These are the exercises we asked you to do. You can look at the different threads. If you've debugged Java programs in Eclipse, they should look very familiar. You can look at the different variables. You still have the naming problem. So yesterday, remember, you had to qualify which control block you were looking at. It's still the same kind of issue. You have to do some trickery to find it here. And it doesn't have sort of the nice visual aspect of showing you which code is running on which SPE. And you might not be able to sort of find mailbox synchronization problems. Maybe those things will come in the future, and in fact, they likely will. But a lot of that is sort of still lacking. So what do you do in the meantime, in the next 2 weeks as you're writing your programs? So I've looked around for, some tips or some talks and lectures and what people have done in terms of improving the process for debugging parallel codes. And probably the best thing I found is this talk that was given at University of Maryland on defect patterns. And so it was just the rest of these slides are sort of largely drawn from that talk. And I'm going to identify just a few of them and sort of give you some examples so that you can understand what to look for and what are some common symptoms, what are some common prevention techniques. So the defect patterns, just like the programming patterns we talked about, sort of meant to help you sort of conjure up the right contextual information in your head. What are things you should look for if you're communicating with somebody else? What kind of terminology do you use so that you don't have to explain things down to every last detail? And at the end of this course, one thing I'd like to do is maybe get some feedback from each of you as to what are some of the problems that you ran into in writing your programs and how you actually went about in debugging them. And maybe we can come up with cell defect patterns and maybe cell defect recipes for resolving those defect patterns. So probably the worst one of all, and the easiest one to fix, is that you have new language features or new language extensions that are not well understood. And this is especially true when you take a class of students and they don't really know the language, they don't know all the tools, and you ask them to do a project in 4 weeks, and you expect things to work. So there's a lot for everybody to sort of pick up and understand. So you might have inconsistent types that you use in terms of calling a function. There might be alignment issues, which some of you have run into. You might use wrong functions. You know what the functionality you want, but you just don't know how to name it, and so you might use the wrong function. Some of these are easy to fix because you might get a compile time error. So if you have mismatch in function parameters, then you can fix that very easily. Some defects, very natural to parallel programs, might not come up until runtime. So you might end up with crashes or just erroneous behavior. And I really think this is probably the easiest one to fix. And the prevention technique that I would recommend is, if there's something you're unfamiliar about or you're not sure about how to use something, ask. But also, you don't need to know all the functions that are available in something like the cell language extensions for C. Yes, there are a lot of functions. The manual is hundreds of pages, and you can't possibly go through it all, and nobody becomes an expert in everything. But understand just a few basic concepts and features. So we've, David identified a bunch that he's found useful for writing the programs, and some of the ones that are up on the web page under the recipes for this course. List a few more. And so this might help you in sort of just understanding how these functions work, understanding basic mechanisms that they give you, and that's good enough because it'll help you get by. And certainly for sort of doing the project under short time constraints, you don't need to know all the advanced features that Cell might have. Or you can probably just pick them up on the fly as you need them. Okay, so what are some more interesting problems that come up? I think one that is probably not too unfamiliar is the space decomposition problems. So if you remember, space decomposition is really data distribution. You have a serial program that you want to parallelize, and what that means is you have to actually send data around to different processors so that each one knows how to compute locally. And here you might get things like segmentation faults, alignment problems. You might have index out of range errors. And what this comes of is sort of forgetting to change things or overlooking some simple things that don't carry over from the sequential case to the parallel case. And so what you might want to do is sort of validate your distributions and your memory partitions correctly. So what's an example? So suppose you had sort of an array or a list of cells. Each cell has a number. And what you want to do is, at each step of the computation, for any given cell, you want to add the value to the left of it and the value to the right of it. So here we have cell 0 has the value 2. We'll assume that the end is connected to the first, so this is like a circular list, a circular buffer. So adding the left and right neighbor would get me, in this case, 3 plus 1, 4, and so on and so forth. So, and you want to repeat this computation for n steps. So this might be very common in computations where you're doing near-neighbor communication. So what's a straightforward sequential implementation? Well, you can use two buffers, right? One for the current time step, and you do all the calculations in that. And then you sort of use another buffer for the next time step, and then you swap the two. And so the code might look something like this. Sequential C code. My two buffers, here's my loop. I write into one buffer, and then I switch the two buffers around. Any questions so far? OK. So now, what are some things that can go wrong when you try to parallelize this? So how would you actually parallelize this code? Well, we saw in some of your labs, for example, that you can take a big array, split it up into smaller chunks, and assign each chunk to one particular processor. So we can use that technique here. So each processor, we have n of them, or rather size of them, and it's going to get some number of elements. And so at each time step, we have to compute locally all the communications, but then there's some special cases that we need to treat at the boundaries, right? So if I have this chunk and I need to do my near-neighbor communication, I don't have this particular cell, so I have to go out there and request it. And similarly, somebody has to send me this particular data item. So there's some data exchange that has to happen. So in the decomposition, you write your parallel code. Here, each buffer is a different size. And what you do is you have some local, which says this is how much of the data I'm getting. So n is the total number of elements, size is the number of processors. So n local essentially tells me the size of my chunk. And I'm iterating through from 0 to n local, and I'm doing essentially the same computation. So what's a bug in here? Anybody see it? Sort of giving you some hints. There's things highlighted in red, or there's something wrong with the things highlighted in red. And as another hint, so this is essentially the computation that's going on at every processor. This is my buffer. and at every step I have to do the calculations, taking care of the boundary edges. Anybody wants to take a stab? Omar?
Is it that next buffer 0 needs to look at data from another?
Next buffer 0, right. So what might be a fix for that? So next buffer 0, so if this is 0, then buffer of x minus 1 plus this points to what? So here's the...
So you need to start at 1 and go to
right,
local minus
exactly. To local plus 1, because you're going to do the... So that's one bug. The other thing is sort of the assumption that your data elements might be divisible by the number of processors that you have. So you picked a decomposition that might not be symmetric across all processors. So it's a more subtle thing to keep in mind of. So that's one particular kind of problem that might come up when you're decomposing data and replicating among different processors. So you have to be careful about, what are your edge case, what are your boundary cases going to be, and how are you going to deal with those. A more difficult one is synchronization. So synchronization is when you're sending data from one processor to the other, and you might end up with deadlock. Because one is trying to send, the other is trying to send, and neither can make progress until the other is received. So your program hangs, you get non-deterministic behavior or output. Every time you run your program, you get a different result that can drive you crazy. So some of the defects can be very subtle. You might not, this is probably where you'll spend most of your time trying to figure it out. And so one of the ways to prevent this is to actually look at how you're orchestrating your communication and doing it very carefully. So look at, for example, what's going on here. So this is the same problem. And what I'm doing is now this is the parallel version, and I'm sending sort of the boundary cases, the boundary cells, to the different processors. And this is an SPMD program. So an SPMD program has every processor running essentially the same code. So this code is replicated over n processors, and everybody's trying to do the same thing. So what's the problem with this bug, with this code? We're doing a send of next buffer 0, and here rank essentially just says each processor has a rank. So this is a way of identifying things. So I'm trying to send it to my previous guy, I'm trying to send it to the next guy, and here I'm sending the value at the far extreme of the buffer to the next processor and then to the previous processor. Anybody see what's wrong here?
So are these blocking?
Yeah, imagine they're blocking sends. Right. So this will deadlock. Right. So this will deadlock because this processor is trying to send here, this processor is trying to send here, but neither is receiving yet, so neither makes progress. So how would you fix this? And as was pointed out, you might not want to use a blocking send all the time. So if your architecture allows you to have different flavors of communication, so synchronous versus an asynchronous, a blocking versus a non-blocking, you'll want to avoid using constructs that can lead you to deadlock if you don't need to. And the other mechanism, this was sort of pointed out briefly in the talk on parallel programming, you want to order your sends and receives properly. So alternate them. So you have a send in one processor, a receive in the other. And you can use that to sort of prevent deadlock and get the communication patterns right. There could be more interesting cases that come up if you're communicating over a network where you might end up with cyclic patterns leading to loops. And that also can create some problems for you. The last two I'll talk about aren't really bugs in that they might not cause your program to break or compute incorrectly. Things might work properly, but you might not get the actual performance that you're expecting. So these are sort of performance bugs or performance defects. So a side effect of parallelization is often the case that you're focusing on your parallel code, and you might ignore things that are going on in your sequential code. And that might lead you to essentially, you've spent all this time trying to parallelize your code, but your end result is not getting the performance that you expect because things look sequential. So what's wrong here? So as an example, imagine that we're doing, instead of reading data from so in the previous case, I didn't show you how we were reading data into the different buffers. But suppose we were getting it from some files, so input buffer. So now we have an SPMD program again. Everybody's trying to read from this buffer. What could go wrong here? Everybody have an idea? So every processor is opening the file, and then it's going to figure out how much to skip, and then it'll start reading from that location. So everybody's reading from a file, so that's OK. Nobody's modifying it. But what can go wrong here?
Well, everyone's reading from the file, so they have to take turns because whoever is just locked
Right.
is first.
Right. So you essentially sequentialize your execution because reading from the file system becomes the bottleneck. So you'll want to schedule input and output carefully. And you might find that not everybody needs to do the input and output, right? Only one processor has to do the input, and then it can distribute it to all the different processors. So in the master-slave model, which a lot of you are using for the cell programming, the master can just read the data from the input file and distribute it to everybody else. So this avoids some of the problems with input and output. And you can have similar kinds of problems if you're reading from other devices. It doesn't have to be the file system. So here's another one, a little more subtle. So you're generating data. Hey, Alan, what's up?
Question on that last slide. I somehow missed the distinction between waiting for the master to read all the data and distribute it and waiting for the other processors to get through so I can read my part of the data. Isn't that going to be about the same time on this system?
No, so here just essentially the master reads the file as part of the initialization, right? And then you distribute it. So the distribution can happen at runtime. So it's the initialization you don't care about because hopefully that's a small part of the code. And so in this code, only the so this code is guarded by rank equals master, so only it does this code. And then here you might have a command that says wait until I've received data and then execute. Or on the cell, then these might be the SPE create threads that you happen after you've read the data. So hopefully the initialization time is not something you're concerned about too much. So if you're generating data on the fly or dynamically, so here we might use the srand function to sort of start with a random seed and then fill in the buffer with some random data. So what could go wrong here? So in srand, when you're using a random function, sorry, this is a typo. This is the same function. When you're using a random, a pseudo-random number generator, you have to give it a seed, and if everybody starts off with the same seed, then you might end up with the same random number sequence. And if that's something you're using to sort of parallelize your computation, you might in effect end up with the same kind of sequence on each processor, and you lose all kinds of parallelization. So there's some hidden serialization issues in some of the functions that you might use that you should be aware of. Okay, and the last one I'll talk about is a performance scalability defect. So here you parallelize your code, things look good, but you're still not getting the, you've taken care of all your I/O issues, but you're still not getting the performance you want. So why is that? You might remember your Amdahl's law, and what you want is an efficiency that's linear. So every time you add one processor, you want sort of an equivalent number. You want a straight line curve between the number of processors and speed up. So it should be a linear relationship. So you might see sublinear speedups, and you'll want to figure out why that is. And some of the common causes here, and this will be sort of the in-depth focus of the next talk, is unbalanced amount of computation. Remember, dynamic load balancing versus static load balancing. Your work estimation might be wrong, and so you might end up with some processors idling, other processors doing too much work. And so the way to prevent this is to actually look at the work that's being done and figure out whether it's actually roughly the same amount of work everywhere. And here you might need profiling tools to help. And so I'm going to talk about this in a lot more detail in the next lecture. So in summary, there are lots of different bugs that you might come up with. There's sort of a few that I've identified here, some common things you should look out for. So the erroneous use of language features to understand only a few basic concepts of the entire language extension set that you have. Space decomposition, side effects from parallelization. Don't ignore the sequential code. And then the last one is trying to understand your performance scalability. But there are other kinds of bugs, like data races, for example. So what can you do with those? So remember, data races, you have different concurrent threads, and they're trying to update the same memory location. And so depending on who gets to write first and when you actually do your read, you might get a different result. So with data race detection, these things are actually getting better. There are tools out there that will essentially generate traces. as your program is running. So for each thread, you instrument it, and you look at every load store that it executes. And then what you do is you look at the loads and stores between the different threads and see if there's any intersections, any orderings that might give you sort of erroneous behavior. And so this is getting better. It's getting more automated. Intel Thread Checker is one example. There are others. And I really think the trend in debugging will be towards trace-based systems. You'll have things like checkpointing. So as your program is running, you can sort of take a snapshot of where it is in the execution, and then you can use that snapshot later on to sort of inspect it and see what went wrong. I think you might even have features like replay. In fact, some people are working on this in research and in industry. So you might be able to say, oh, something went wrong. Here's my list of checkpoints. Can you replay the execution from this particular stage in the computation? So it helps you sort of focus down on, in the entire lifetime of execution, on a particular chunk where things have gone wrong. And this is sort of a personal dream. I think one day we'll have the equivalent of a TiVo for your programs. And you can use this for debugging. So my program is running, something goes wrong, I can rewind it, I can inspect things, do my traditional debugging, change things maybe even, and then start sort of replaying things in the, and letting the program execute. And in fact, we're working on things like this here at MIT and with collaborators elsewhere. So this was sort of a short lecture. We'll take a break. You can do the quizzes. A note on the quizzes, there are two different kinds of questions. They're very similar, just one word is different. And so you'll want to just keep that in mind when you're discussing it with others. And then, about 5-10 minutes, and then we'll continue with the rest of the talks, lecture 2. Thanks.